Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So this week I really wanted to focus on how we can go about writing code in C++ to implement the technique of Gauss-Jordan elimination for the purposes of inverting a matrix, as we talked about in the previous episode. If you've seen the previous episode already, you'll know what I'm talking about. We spent quite a lot of time just going over the theory behind the technique of Gauss-Jordan elimination and really covering how it works and working through a couple of examples by hand so that we could get a feel for how the technique actually operates. If you haven't seen that video already, I suggest you do so before watching this one if you're interested in the theory behind the technique anyway. I'll put a link to it in the description below, and I'll put a link up here on the screen somewhere as well, so you can go and check that video out if you want to. So from an algorithm point of view, Gauss-Jordan elimination is actually a particularly interesting problem. From the video last week when we went over the theory, you'll see that it's one of those processes that is actually quite straightforward to do by hand, when you can look at the problem and you can make decisions based on your judgment and your experience and things like that in order, to decide which of the elementary row operations to use and when in order to get to the result that you want. But to actually create computer code to allow a computer to do that in an algorithmic fashion was, in my opinion, a really interesting problem, and I spent quite a bit of time on it, and I've come up with a solution that works. It's definitely not the only way of doing it. I'm sure there are other ways that algorithms could be created to solve the same problem, and my technique may not even be the most efficient, but it does work as far as the testing that I've done would indicate. As this is quite a long video already, I'm going to really keep the introduction short. I'm just going to say, as I always do, that if you like this video, please remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future episodes. I do try and make a video once a week, so if you subscribe, you don't need to worry about missing anything. Okay, right, so without much further ado, I suggest let's jump to the computer and let's have a look at the code of how we can go about implementing Gauss-Jordan elimination. Okay, so I just wanted to begin our video today with a very quick recap on some of the core ideas from the previous video. I'm not going to go over that in any great detail. If you haven't seen the previous video already, where we talk about the theory of Gauss-Jordan elimination and go over mathematically how it works, then I really suggest you go and look at that video now. As I said in the introduction, there will be a link to that in the description below. However, I will just very quickly recap just so that we're all on the same page before we really start to look specifically at the code that I have created to implement this. So the first thing that we talked about last week was Gaussian elimination and how this is a way that we can use for solving systems of linear equations. And in particular, the aim of this is to transform a given matrix A into what we call row echelon form, or sometimes called the upper triangular matrix, which will look something like this. So all of the lower left-hand elements are 0, all of the leading elements across the diagonal are 1, and then all of the non-zero elements that are not the leading elements are concentrated in the upper right corner. Okay, and that is then said to be in row echelon form. And we transform the matrix into that using the three elementary row operations of add a multiple of one row to another, multiply a row by a non-zero number, and swap one row with another one. Okay, then we use those operations to transform our given matrix into that form. We then went on to talk about Gauss-Jordan elimination and the matrix inverse, and how this essentially takes the process further to give what we call reduced row echelon form of the matrix, where all the leading elements are 1 along the diagonal and all the other elements of 0. And we talked about how we augment the identity matrix onto the matrix we want to inverse, and then our aim is to go from something like this, where we have the matrix that we want to inverse here shown in blue on the left, and the identity matrix that we've attached onto that, or augmented onto that on the right in white. And our aim is to transform this matrix into something that looks like this. So we want to perform elementary row operations to transform this blue half of the matrix into the identity matrix that we see here. After we have done that, then the values that we have over here on the right, shown in yellow, b11 to b33, will now be the elements of a to the minus 1, or the inverse matrix. So b11 to b33 will now contain the inverse of the matrix that we started with. And we then went on to talk about actually how that process works and everything else. But what I want to focus on today is how we can go about actually implementing this in C++. Now, as I mentioned in the introduction, this is really a very interesting exercise, because this is one of those algorithms that's relatively easy to do by hand when you can look at it yourself and you can see and make judgments about what operation, which of the row operations to do and when. But it becomes slightly more difficult to think about how to actually write an algorithm so that a computer can do that. But that's what we're going to focus on today. Now, the first thing that I want to look at is that we need, obviously, to extend our QB Matrix 2 class that we created in the first episode on this linear algebra series. And we need to add functions to perform the elementary row operations and one or two other housekeeping activities that we will need in order to make the inverse work. Now, what I'm going to do is I'm going to go through and talk about each of these functions that have been added to the code, and then I'm going to come back and actually talk about how the algorithm itself is implemented. So each of these functions are essential to make the algorithm work. So we'll talk about those first, and then we're going to come back and we're going to actually have a look at how the algorithm itself works. Okay, so from here, I suggest that we jump into the code. We're going to talk about the functions I've added to swap two rows in the matrix, to multiply a row by a given number, to multiply a row by a given number and add the result to another row, to find the row with the maximum element in any given column, to join two matrices together column-wise, and to separate a matrix into two matrices around the specified column. Now, the reason for all of these, I mean, I think these are obviously the first three of the elementary row operations that we've talked about, and I think the need for these others, and there are one or two others as well, will become clear as we go through. So this is what we have, and some of this code is, of course, exactly the same as we talked about before when we created the QB Matrix 2 class in the first episode on this linear algebra series. And some of it obviously has been added. So I'm going to go through and we're going to talk about what's been added. Now, the first thing that has changed is I've added a bunch more includes here. So we bring in std exception for doing exception handling. We'll see why we need that in a moment. I've also brought in IOStream and IOmanip that we can use simply because I've brought the print matrix code from the test code that we wrote originally into this class so that we can use it. That's really more for debug than anything else, so not essential. And we bring in math.h, and we also need the vector class. That will become clear later on when we go on to talk about testing this code. Okay, so apart from that, the first thing that we've added is a new constructor here. So we have one new constructor that accepts a number of rows and number of columns as integers, and then accepts the input data in the form of an std : vector object of type t. Okay, now we talked about templates and how all that works in the first episode in this series, so I'm not going to talk about that now. But we have this new constructor, and we can have a look at the code for that first. Where is it? Yep, so this really just does the very basic thing, simply copies n rows and then calls into the relevant internal variables, computes the number of elements, allocates memory for n matrix data, and then simply copies the data from the instance of the vector class pointed to by the input data pointer. So that's that line there. So that's pretty straightforward. If you look back to the function declarations here, there are a number of other things that we have added. Okay, so the first one here, set to identity. So the purpose of this is to transform the given matrix into the identity matrix, so we can use that to create an identity matrix when we need one. We've obviously then added a function to perform the inverse. Now, we're not going to talk about that at the moment. We're going to come back to that. And I've also made some modifications to the equality, the overloading of the equality test operator. We're going to come back to that. And I've also added another function called compare that allows us to specify a tolerance. So this allows us to compare the current matrix with another one to a specified degree of tolerance of whether they're equal or not, rather than testing for exact equality. It's often the case, specifically if you're using double precision floating points, it's often the case really that you will not get exact equality, and so an exact test for equality will fail, but the numbers could be, the same to, 1 times 10 to the minus 27 or something like that, but it would still fail if you did an exact test. But obviously for all real purposes, they're clearly going to be close enough. Okay, so we haven't changed any of the other overloaded operators. We brought in one more public method called separate, which is the function to separate a given matrix into two matrices, and this accepts as input two pointers to QB matrix 2 instances, and the column, an integer for representing the column number about which we want to perform the separation, and it returns true or false whether it's successful or not, and it puts the results into the two matrices pointed to by those pointers. Right. We then have a whole bunch of private functions now. At the moment these are declared public, which I've done just for testing. These should otherwise of course be private. Sub to ind we talked about before, so we don't need to mention that. Now is square, that's a very simple Boolean function that returns true or false depending on whether the current matrix is square or not. That's easy. Close enough is a function we're going to talk about. This compares two numbers, both of type t, and sees if they are equal to a specified tolerance. Now we'll talk about that again a bit later. Now we have swap row. This is the function that swaps row j with row I. Okay, so the row number is indicated by the integers I and j. Mult add will take the contents of row j, multiply it by mult factor and add it to row I, and mult row simply multiplies the row indicated by row I by the mult factor variable there. Join to join two matrices together, so that joins whatever matrix is given here by this input to the existing matrix. Find row with max element finds the row with the maximum element in the given column for a specified starting row, so it doesn't necessarily scan the whole matrix, and print matrix as well, we talked about before, just for doing nice display. Okay, and that's pretty much everything there that's changed. So if we have a look at the specific functions themselves, so we haven't changed anything there. So set to identity, this is the first one. So the purpose of this is simply to turn the given matrix into an identity matrix. Now obviously if the matrix is not square, so we use the isSquare function there. So if not isSquare, and then we throw this exception. This is why we included the std exception, because that's an invalid argument essentially, and we have a message would go with that cannot form an identity matrix that is not square. Assuming the matrix is square, we simply loop over all the rows and the columns, and if column is equal to row, meaning we're on the diagonal, then we set the element to 1, otherwise we set the element to 0. That will obviously go through and create the identity matrix. Okay, so these we all had before. Now this is compare, which compares matrix 1 to the given matrix to within a certain tolerance. And the first check we do obviously is if the dimensions are the same. If the dimensions of the matrices are different, then obviously they're not the same, so there's no point doing anything else. We then define a cumulative sum. Now we're doing this as the sum of squared differences, and we then loop over all of the elements, and we simply extract element 1 from matrix 1, the input matrix, and we extract element 2 from the current matrix, and then we simply perform a cumulative sum of the squared differences of those, and then we take the square root of that divided by the total number of elements minus 1, which gives the final value. And if that final value is less than the tolerance, we return true. If not, we return false. So that's a fairly straightforward way of doing things. Okay. Now, the overloaded operators, we haven't really added any of those. The one that I did change was the equality operator. So what's slightly different here, but previously we checked that whether the current element in the existing matrix was exactly equal to the right hand side input matrix there. And what I've done is I've changed that to use this close enough function. So now we say if it's not close enough, then we return false, otherwise we return true. So that's the only change there. And let's just skip ahead a little bit and have a look at the close enough function. It's very simple. It's just simply this. Simply accepts two inputs of type t, and it returns the floating point absolute value of f1 minus f2 less than 1 times 10 to the minus 9. So that's the fixed tolerance. So we compare if these two numbers are equal to within this particular tolerance. If f1 is close enough to f2, then we accept it. So obviously we could use that to test if a number is close enough to 0, for example, or whatever. Okay, so let's go back up, and that's the overloaded operators. Okay, we then have our function to separate a matrix into two parts. Now this is one of those things, the need for this will become clear later on when we actually go to talk about the actual specific algorithm itself. It accepts, as I said, two pointers to QB matrix 2 objects as input and an integer for the column number. The first thing that we need to do is to resize the two matrices that we have pointed to by these pointers to match the dimensions that we want. Okay, so we know that the number of columns, number of rows is going to be the same as the matrix we already have, so that's easy. The number of columns in matrix 1 is simply going to be equal to column number, whatever this is, we have that many columns. And then the number of columns in matrix 2 is simply going to be the total number of columns minus column number. Okay, so we resize the two matrices that we've been provided with as input to match those dimensions, and of course the resize operation resets all the elements in the matrix to 0, so that's good. We then loop over all of the elements in our original matrix, and we simply set the element in matrix 1 or matrix 2 depending on where we are. So if column is less than col num, then we set the element in matrix 1, and if not, we set the element in matrix 2. And I think you can see how that's working. We're just using the set element method with row and column and extracting the current element from the current matrix. So that's really very straightforward. And the result of that will be to take whatever data we have in our existing matrix and copy it into two smaller matrices, with the separation occurring around the column indicated by col num. So that's fairly straightforward. Now the contrast to that, of course, is a method to join two matrices together. Again, the need for this will become clear when we come to talk about the algorithm. In fact, we've already mentioned it, the need to augment the matrix we want to invert with the identity matrix, and that is exactly what we're going to use this for. So this accepts as input a reference to a QB matrix 2 object that we want to join to the existing matrix, and it simply calculates, extracts the number of rows in the existing matrix and the number of rows in the matrix we want to join to, or join with our existing one, and the same for the number of columns. If they have different numbers of rows, then this operation makes no sense. Now this is very specifically joining a column-wise join, so we're putting the second matrix to the right of the existing matrix. So obviously both matrices have to have the same number of rows, otherwise we throw the invalid argument exception. Okay, allocate memory for the new result, which is simply going to have number of rows times numcols 1 plus numcols 2. That's going to be the new number of elements, so we allocate memory for that. And then we copy the two matrices into the new one. So we simply loop over all of the elements of the new matrix, and we compute the result linear index. Now we talked about this linear indexing in the first episode on this series on linear algebra, so I won't talk about that now. And for whether if j is less than numcols 1, so the current column we're considering is within the first matrix, so we know we're in the left-hand matrix, so we get the data from the left-hand matrix and put it into the new one. Otherwise we must be in the right-hand matrix, so we get the data from there, and we have to compute a new linear index for each one of those accordingly, obviously, because the linear index for each of the matrices will run from 0. Okay, so we can't just use the value of j. And then we simply store the result into the element indicated by result linear index. Okay, I think that's reasonably straightforward. And then just to go through and update the stored data, store the new number of columns, the new number of elements, delete the existing matrix data, and then reallocate it. So this is important. This was actually a bug that I didn't notice before when I first wrote this code. After we delete it, of course, we have to reallocate a new pointer for m matrix data of the new number of elements, and then we simply loop through all of the elements and make a copy of those into m matrix data, like so. Yes, okay. And one point to note, I have clearly forgotten that we should also delete new matrix data there as well. Okay, so after we've done that, we put that here, delete new matrix data, just like that. Okay, a minor change, but yes, there we go. It's funny how you spot things when you go through and try and talk about it to someone. Now we have the code that actually does the inverse itself. Now I'm not going to talk about that now, so we'll skip over that, and we're going to come back to it later. In the private functions, we have sub to ind, we talked about that before. Now we have our code for the is square, returns a boolean, true or false, if the matrix is square. Very simple, simply compare the number of columns to the number of rows. If they're the same, return true, otherwise return false. Very simple. And this is our function to swap rows I and j, and all of these operations work in place because I think that's a lot quicker. Okay, so the first thing we do is we store a temporary copy of row I. So we allocate memory for temp row with the number of columns, and then we simply scan across those columns. We loop through each column, variable k here, okay, along row I, and we store those into our new temporary variable. We replace row I with row j, so again we loop through the columns and we set the contents of row I to be equal to the contents of row j, and then we simply replace row k with the temporary copy. Oops. Yes, my spelling's not the greatest in my code anyway, with a temporary copy of the original row I, just like so, and that's everything we need to do. And then just before we finish, we delete temp row. Okay, so that's pretty basic to swap the row j and row I, to swap those around. Okay, the other one is mult add. This adds a multiple of row j to row I, again in place, and all we're going to do is simply loop through all of the columns, and then we set the contents here of m matrix data. We use the sub2in function of I and k, so I is the row number, k loops through every column, simply to plus equals whatever the contents of the jth row is at that column multiplied by the multiplication factor. Pretty simple. And a function to find the row with the maximum element from the starting row to at the specified column number. So we store a temporary variable called temp value, and we start at starting row column number. Okay, and then we simply set row index to starting row, and then we loop through from starting row plus 1 to mn to the total number of rows. And if the absolute value of the difference, if the absolute value of the element in our matrix there is greater than the temp value that we've stored here, then we store the row index of k, and we update temp value accordingly. It's a standard algorithm to find a maximum. Okay, so every time we find a value that's bigger than temp value, we copy it into temp value and update row index, and then obviously that's going to scan down the column of the matrix from starting row and will identify the value of the maximum and also its index. Then we simply return its index. That's all we're interested in. We want to know the row with the maximum element. Okay, so fairly straightforward. Mult row, this multiplies the given row by the provided multiplication factor. It's very simple, simply loops through all of the columns and uses this m matrix data sub2int I k, so scans along the row for every column k and multiplies that by multiplication factor. So mult equals, yep. Pretty simple. Print matrix we talked about before, so I just lifted this code out of the test code that we wrote originally and brought it into this class, so it simply prints out the given matrix. The only difference here is I'm obviously using this there to indicate that we need to work with the current matrix. Okay, so that is actually all of the basic code. Those are all of the functions that we use to create our algorithm. The challenge then is, how do we string all that code together to actually create an algorithm that works? Well, let's just talk about exactly what we're going to do. Now, this is where it gets really interesting in my view, because obviously when we look at this and we do this kind of operation by hand, it's relatively straightforward. You can make decisions based on intuition and experience and whatever about which row operation to perform next. However, the computer has to process it in an algorithmic and orderly fashion. So the basic algorithm is, if we're starting with a matrix, something like this, as just an example, the first thing we're going to do is we're going to consider the first leading element on the diagonal, shown here in orange, okay? And we're going to use row operations to make sure that that element is set to 1, okay? We're then going to consider all of the elements in that column apart from that one, so I've shown those in blue, and we're going to use row operations to make those equal to 0. And then we will consider all of the elements in that row apart from that one, so here shown in blue. And as before, we will use row operations to try to make all of these equal to 0, okay? And then we're going to move on to the next diagonal element, and we're going to use row operations to make that value 1. And then we consider the other elements in that column, and we make those equal to 0, and we consider the other elements in that row, and we make those equal to 0, and so on throughout the the matrix. Now what that actually looks like, if we put that into a flowchart, we have this. Now I don't always go for flowcharts for explaining algorithms, but since this one is a little bit more complicated, I thought it would be worthwhile. So this is the overall flowchart of the algorithm. So we start obviously from start. The first thing we need to do is to test whether the matrix is square. If it isn't, then we end. We can't invert a matrix that isn't square, so clearly there's no point going any further. If the matrix is square, we come down to here and we augment it with the identity matrix of the same dimensions. We then set diagonal index to 0, and we're going to loop diagonal index along the number of rows. So we have here, if diagonal index is less than number of rows, if it isn't, then we go to stop. So if we've reached the end, well, we'll come back and we'll talk about that later. So if assuming the diagonal index is 0, so it's definitely less than the number of rows, the first thing we're going to do, we set C row equal to diagonal index, and we set C col equal to diagonal index. And then we're going to find the row which has the maximum element in C col. Now that's the function that we just talked about. Now if that is the current row, then we don't need to do anything. If it isn't, we want to swap rows. So the purpose of that is to bring the largest element in that column into the current row. Okay, and then we do a test. We have a look here, so whether we've swapped rows or not. We test whether the elements, so throughout these let me just explain with these flowcharts, where I put elements like this in square brackets, I mean we look at the element of the matrix at that row and column. Okay, so we then test whether the element of the matrix at C row C col is equal to 1. If it isn't, we then perform this operation to make it equal to 1. So we're multiplying it by 1 over whatever it is. So we take all of the elements in C row, so that's C row comma star, so all of the elements in C row multiplied by 1 over the element at C row C col. Okay, so that is going to make the element at C row C col equal to 1, and it's going to do other things obviously to all of the other elements in that row. Now if once we've done that, we then go to here, or in the case that this element is already 1, then we come back to here. Now process rows and cols, I put a double star here because this is quite complicated. Now I have separate flowcharts to explain what we do for the rows and the columns. So as we just saw in the example, we first go through all of the rows in the column apart from the current element, and we want to make those equal to 0, and then we look at all of the columns in the row and we want to make those equal to 0. So we're going to come and look at those flowcharts for that in a moment. Okay. We then, once we've done that, we've processed the rows and the columns, we increment diagonal index, and we come back to here. So you can see that forms a loop. We're going to loop through here. Every time through here we increment diagonal index, and so we will go through and we'll consider every element along the diagonal, all the leading elements, and we'll process the rows and cols and everything below them. Now once that loop finishes, once we've processed every element, we've got to num rows, so we drop out to here. Now what we're going to do is test if the left hand side of the matrix, now remember that what we did was to take the matrix we want to invert and we augmented it with the identity matrix on the right hand side, and what we want to see, if the left hand side is now equal to the identity matrix, then we know that we've finished. So if the left hand side is equal to identity matrix, yes, end. That's the objective, is to turn the left hand side into the identity matrix, and once we've achieved that, the right hand side will contain the inverse matrix that we want. So if we've gone through all of that loop and that still hasn't occurred, we go back to here, we reset diagonal index to 0, and then we repeat the process again. And the way the algorithm works is it will keep doing this process until this condition here is met. Or in reality, we also implement a counter, of course, so that we don't let it just run forever. There will be situations, there are some matrices that simply cannot be inverted, even though they're square. Of matrices that are close to singular or singular can't be inverted, so there are some matrices that we can't do this operation for, and so in some situations this algorithm, it will simply run and run and run and run, and it will never be able to achieve this result. So in reality we have to implement a counter to prevent that from happening. So once we reach the condition where the left hand side is equal to the identity matrix, or our counter exceeds some threshold value, we will drop out and end. Okay, so that's the overall flowchart. I suggest take a bit of time just to have a look at that, pause the video if you need to, and have a look at that, and I think it will help to understand the code when we come to look at it in a moment. Now I mentioned there are separate flowcharts for processing the rows and the columns. Okay, so this is the flowchart for the column operation. So starting point, we start here obviously, and we have as input to this process C row and C column. So this is the position in the matrix of the current element that we're considering. We then set a variable called row index equal to C row plus 1, and then we see if row index is less than a number of rows. Obviously that's going to implement a loop. If it is, then we finish. If it isn't, then we go down to here. We check if the element there is already 0, because if you remember, what we're trying to do is we go down the rows of this column as we want to make each element equal to 0. If it's already equal to 0, then obviously we don't need to do anything. So it makes sense to test that first. So we test the element of the matrix given at row index C col. If that's equal to 0, we simply go here, we increment row index, go back to here, and we go through the loop again. If it isn't, we then compute a variable called row 1 index. We simply set that equal to C col. Okay, so row 1 index is simply going to go along the corresponding leading element for this particular row. Okay, and then set row 1 value equal to the element of the matrix given by row 1 index C col. And if that's equal to 0, we don't do anything because we can't work with that. So the objective is to make this element at row index C col equal to 0. And we have to do that by manipulating one of the values from another row. So if row 1 value, if it's already equal to 0, we can't do anything, so we just ignore it. And we skip back to here, increment row index, and go back through the loop. Now if it's not equal to 0, we go to here. We extract the value at that location. So the current element value is row index C col. Okay, so that's this position, right? So we extract its value. We then compute a correction factor, which is going to be minus, or the negative, of the current element value divided by row 1 value. Okay, so the point of this is to make a number, the correction factor, that when we multiply the row at row 1 index by this number, the element is going to exactly cancel out the element that we want to set to 0. Okay, and so the point is we're working down the rows of the column, and we want to set each element in the column to be equal to 0, and we need to do that by adding some number to it, and we have to get that number from some other row, and we have to do this using the elementary row operation. So this is the operation where we take one row, we multiply by a correction factor, and then we add that to the existing row that we're dealing with. So we need to calculate the value of the correction factor such that when we multiply the row given by row 1 index by that correction factor and then add that to the row given by row index, it will make the element in the current column, C col, that we're considering equal to 0. That's the objective. And then once we've done that, we simply loop back around here, increment row index, and continue. Okay, so that will go through the column and perform that operation. We then have a virtually identical flowchart for the row operation, and the only difference here basically is we swap row for column, and we're now looping through every element along that row. Okay, and then doing exactly the same thing. So I'm not going to talk about that too much. Now, I think that's perhaps a little bit confusing from the flowcharts, but I really do hope that when we come to look at the code in just a moment, that this will make a lot more sense. But I thought it would have some value to show the flowcharts first, simply to give an overview of really what's going on. So, you know, take your time, pause the video if you want to, have a look at these flowcharts and study them. And hopefully then when we talk about the code, which we're going to look at just now, it will make a bit more sense. So let's have a look at our code. If we go back to our QB Matrix 2 class, now we've talked about all of the new functions that we added, except for obviously the function to compute the inverse. Let me just find where I put it. Okay, compute matrix inverse, here we are. So this is the function that really does the work. This implements the algorithm that we've just been talking about in the flowcharts. And I have to confess, was actually a really interesting exercise to put this algorithm together. And I must emphasize, of course, this is code that I've put together to solve the particular problem that I need to solve. The testing and everything that I've done, it does seem to work. We're going to talk about that in the next video. You know, but if you go on to use this code as I've written it here, do be aware to make sure that you test it thoroughly. Be aware that, of course, it may still contain bugs despite every effort I've made. And you know, just be sure to make sure that you know, it is actually appropriate for what you want to do. Anyway, so the first thing we need to check, obviously, is our matrix square. If it's not, we throw an invalid argument exception because we can't compute the inverse of a matrix that is not square. If we get past that, then we know the matrix is square and we can continue. So the first thing we need to do is to form an identity matrix with the same dimensions as the matrix we wish to invert. And we do that, we simply create a new QB matrix 2 object called identity matrix of the same size of the matrix that we have, and then we use the set to identity function that we've just talked about to make that an identity matrix. We're then going to join that identity matrix to the existing matrix. Okay, so we store our original number of columns, we'll need that later, and then we use the join function to join identity matrix to the matrix that we're speaking about, to our current matrix. And obviously that will modify the number of columns, which is why we need to store the original. Okay, and we're then going to begin the main part of the process. We initialize C-row and C-col for current row and current row and current column. We set our max count to 100, so I mentioned that we don't let the algorithm just loop forever in conditions where it works, so we set the threshold to 100 iterations. If it hasn't achieved the right result by then, we finish. And we set count to 0. We're going to need count, obviously, to check that. And we set complete flag to false. So complete flag, just a Boolean variable we're going to use to detect when the process is finished. We're then going to loop. So while complete flag is false and count is less than max count, we loop through this process. And each time through that loop, we are going to loop diagonal index from 0 to the number of rows. Okay, so we talked about that on the flowchart. We set C-row and C-col both equal to diagonal index. Okay, so the effect of that will be that C-row and C-col will be the indices of all of the leading elements of our matrix. We then find the index of the maximum element in the current column using find row with max element. Okay, so we want to find the row with the maximum element in the current column starting from the current row. Okay, so we're only looking from the current element and below in the matrix. We're not interested in what's going on above it. Okay, and we get that into an integer called max index. And we then test if that is the current row. Okay, if it isn't, we're going to use the swap row method to swap them around. So if max index is not equal to current row, then we call swap row with current row and max index. Okay, so that would be to swap those two around. Now I've commented out these cout statements here. The purpose of these is you can have essentially a verbose mode, which simply shows all of the steps that the algorithm is doing. So when we come to actually look at testing it in a moment, I'm going to put those back in and we'll be able to see actually what's going on. We then make sure that the value at C-row C-col is equal to 1. This is the objective. You know, we want all the leading elements to be equal to 1. So we check first that it's not equal to 1 already. Obviously, if it's already equal to 1, we don't need to worry about doing anything else. If it's not equal to 1, we calculate our multiplication factor as being 1 divided by the current matrix element. And then we simply multiply the whole row at C-row by that multiplication factor, and that will have the effect of making the current element equal to 1. We then come to the row and column operations that I talked about. So the first thing, firstly we consider the column. Okay, so we're going to loop through all of the rows in this column from the current row plus 1, obviously, to the end. And if the element there is already 0, we don't do anything. So we do this test. If not close enough, and this is where we use the close enough function we talked about. If the current element is not close enough to 0, then we need to do stuff. If it is, we don't worry about it. Okay, so obviously the reason we do this is because we would, if this element was equal to 0, we could get a condition where we have a divide by 0, which obviously makes absolutely no sense at all. Also, if it's very close to 0, then dividing by that can result in very large, unwieldy numbers, which we're not interested in. So it makes a lot of sense to do it this way. So assuming the number isn't close enough to 0, we obtain the element to work with from the matrix diagonal. Okay, as we aim to set all the matrix diagonal elements to 1, this should always be valid for a matrix that can be inverted. This is a really interesting, and this is one of the key points really for me in developing this algorithm, is to decide how to choose which row that we're going to work with in order to set these elements in the current column to 0. And I've done it this way because for any matrix, when I realized that any matrix that can be inverted, it will be possible to make all of the diagonal elements equal to 1. Okay, so if you end up a case where a diagonal matrix is not equal to or is equal to 0, that's the condition that it would cause a problem, then obviously that matrix can't be inverted anyway, so it doesn't really matter. So we simply use row 1 index equals current column. Okay, if you think about it, that's going to give the diagonal elements. Okay, we then extract the value at the current element. Okay, so current element value is equal to the M matrix data at row index and current column. Okay, we get the value stored at row 1 index, that's row 1 index from here, and the current column. Okay, store that in row 1 value. We then test if that value is 0 or not. Okay, so if it's close to 0, we don't do anything. So if it's not close enough to 0, then we're going to compute a correction factor, as I explained just now in the flowchart, which is the negative of the current element value divided by row 1 value. And then we use the multi-add function to multiply the row at row 1 index by the correction factor and add that to the row at row index. Okay, and then we have the cout statement here so we can see what's going on. And then we do pretty much exactly the same process for the row, except now of course we're looping over the columns from the current column plus 1 to the end, and everything else is basically the same except we now use column index. So row 1 index equals column index. We'll still give the diagonals, and then we compute the correction factor and things exactly as before. Okay, so that's that. And then the last thing that we need to do is we need to compare the left-hand side of the matrix to the identity matrix. Now, as we said all along, this process is complete once the left-hand half of the matrix we're working with becomes equal to the identity matrix. So we create two new matrices called left half and right half, and then we use the separate function performed on this, obviously the current matrix, and we pass the references to left half and right half, and this is where we use the original number of columns because we want to split the matrix in two around the original number of columns. So after that we will have left half will contain what should become the identity matrix, and right half, if the left half is the identity matrix, will be the final result. So we do this test, we do if left half is equal to identity matrix. Now remember, I modified the equality operator there so that it doesn't test for absolute equality, it tests that we're close enough, okay, rather than being the absolute. And I set a threshold, I think 1 times 10 to the minus 9 for that. So if we're within, if the difference between the elements is less than 1 times 10 to the minus 9, then we accept it as true. Okay, so assuming that condition is met, then we set complete flag to true. That will cause the while loop to stop the next time around. And we then need to rebuild the matrix with just the right half. So if this condition is met, we've finished. Okay, so that means that the right hand side now contains the inverse. But we want our matrix to be back to the original size. So what we need to do is simply rebuild it. So we set the number of columns back to original number of cols. The number of elements is the number of rows times the number of columns. We delete the previous matrix data, reallocate M matrix data with the right number of elements, and then we simply loop through and we copy the elements of right half that we got from here into M matrix data. Okay, if this isn't met, then we haven't finished. Okay, so we come back to here, we increment the counter, and we go back and we go through the while loop and we repeat the whole process again until this condition is met or count becomes equal to max counts. And then when we come through there, we return complete flag. Complete flag will either be true or false, depending on whether the process was successful or not. Okay, and that is the whole process. Okay, so what I want to do now is have a look at what happens when we run this code. Oh, in fact, actually, before I do that, let's just go back to the test code. So testcode.cpp, this is the file that we put together before, simply to do the testing. I've added a couple of things to this. So when we talked about this before, in the first episode on this series, we brought in functions that we tested matrix multiplication and all of that. We did all of those, tested the equality operator, addition, subtraction, multiplication. Okay, so the first thing what we need to test now is formation of the identity matrix. We simply do that way. We also test joining of two matrices together, and then obviously we test matrix inversion. Okay, and we test that our exceptions work if we try to invert a non-square matrix, and then also we run through a variety, just a small number of tests, okay, where we set these matrices up and then we invert them. Okay, and then we do a bigger one, a 5 by 5, and another 5 by 5. And I've just commented that out for the moment, and testing of a singular matrix, because we're going to come back and talk about that probably in the next video. Okay, so that's testcode.cpp. So if I go back to my terminal window now we're just going to compile that. Right, so we're going to do g++ minus o testcode of testcode.cpp. minus std equals c plus 17. Okay, and then if we run test code, we get all of this. So let's just have a look. Let's just scroll back up. So the first test that we did was test formation of the identity matrix. We can see there that has very clearly given us a 5 by 5 identity matrix, which is joining of two matrices. We've now joined this new matrix of, we started with this new matrix, sorry, of just 0, okay, and we've added to that, or joined onto it, the identity matrix there. So you can see how that join works. It joins column-wise, okay. Separate obviously would divide those two around that column. We then test matrix inversion. We attempt to invert a non-square matrix, and we see that we throw the exception, but we don't want execution to stop. Normally, if we return that code, we would stop with a return code of -1. We then attempt to invert a matrix, so we try to invert this matrix here. Okay, it's 3 by 3 matrix, and we invert, we get that result. Now, I've tested these using other software, and these are the right results. We test inversion of a bigger matrix, so just a 5 by 5 matrix I've made up, which gives those numbers there. And again, I've tested that, those are the right. And another one as well, another 5 by 5 matrix from invert test 3. We go from that to that, and those are indeed the right results. Now, I mentioned about the verbose mode. If we just go back, because this is actually rather interesting. So if we look back in qbmatrix.h, and if we uncomment these lines of code here, okay, for stdc out, and we put this one in as well. And what this will do is allow us to actually see all of the operations that the algorithm is using. So we display a message for swap rows, for multiply row, for multiply, and so on. Okay, so if we go back to the terminal window now, okay, let's just clear that. Let's compile our code again. Now, let's rerun test code. Okay, now so let's just consider this inversion of the bigger matrix. Oh, why didn't that work? Oh, I forgot to save it. Yes, it's always important to remember to save your changes. Okay, so let's compile again. Okay, there we go, and rerun test code. Right, so let's go scroll back up, and we'll consider the initial 3 by 3 matrix. So we're trying to invert this matrix here. Okay, and what this shows is all of the operations that this is doing. So we can clearly see really what's happening. The first thing that we do is we multiply row 0 by a half. Okay, this is row 0, so that will become 1 half and a half. We then multiply row 0 by -1, which will be -1 minus a half, and we add that to row 1. So 1 plus -1 is going to be 0, so we've set that element to 0. This then becomes minus a half, and that becomes a half, and so on. And if you actually follow this through on paper and work it through, I suggest you do that actually. It's quite an interesting exercise, and you can see the operations quite clearly that the algorithm is taking in order to generate the result. It's actually really quite an interesting thing to do. And again, the same for the inversion of the 5 by 5 matrix, but obviously we have many more steps there to get to the final result. Okay, so there we go. We've gone over, that's quite a lot to explain. There's quite a lot of code required to implement this algorithm, but we've looked at the basic flowcharts of the algorithm, and then we've gone on to look at the code that I have implemented to do that. And we've looked at the very basic testing of that algorithm, including the verbose mode, which allows us to see what's going on. And yeah, there we go. That is pretty much how to implement Gauss-Jordan elimination in C++ for the purposes of matrix inversion. So there we go. I think that's really enough for one episode. So we've looked at we've seen the code in C++ that I've implemented to implement the algorithm of Gauss-Jordan elimination, and we've seen then how we can use that as part of our QBMatrix2 class to allow us to compute the inverse of some matrices. What I want to focus on in the video next week is how we can do some more extensive testing of this. Now, I haven't put that together into this video today because I think this video is already long enough. So I thought we'll save that for next week. So next week we're going to focus on how to do more extensive testing to really demonstrate and satisfy ourselves that our code is indeed working the way that it should. So that really just leaves me to say that I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have liked it, please remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Anyway, listen, it's been a pleasure, and I really look forward to seeing you in the next video next week. Thank you very much for watching. Bye.